takes a much longer time than we expect. So please help me to save a time. So when you are dealing with the language model, so there are very well the model, such a language model. Word2Vec is one of them, it's by Google, and the other, there are several existing open source. So we did such a way before. Just forcefully apply the k-mean or k-method while existing the machine learning algorithm or data mining algorithm to the language model, but we didn't get enough good result. However, nowadays with the help of such a language model, so the performance is really increased. Then we can use such a language model, all the translation and the variety of things. Okay? Yes. Can you change it to the slide? Sure. Yes. Oh, it doesn't work. I think because of a high resolution.
Doesn't take to it at all.
It might take a while.
Oh yes, we got it.
Oh, cool.
Yeah.
Okay.
Start. Please.
Okay. So our project is on facial recognition with sort of key features. I'm Scott, Noogie, Damien. So the main aim of this project was to look at different facial features in order to recognize them. So you may recall that we mentioned there's around about 30 to 40 different facial features within a human face. Okay? Okay. So what we aimed to do was to determine if a face was smiling or not, was to determine the gender, and to recognize if there were a member of a given database or group, so just comparison there. There were 3 different models used to try and sort of solve this problem. We've got the self-created model, we've got a model based on FaceNet, and a second model based on VG16 or VGG16 there. There was quite a few iterations to determine the sort of ideal parameters for this. I think it's worth mentioning that with the gender detection, it compared really quite favorably with the a known Kaggle project for that. To sort of deal with this, we used CNNs. These are all different examples of a convolutional neural network.
Which data set has the gender information also?
CelebA. So CelebA was the chosen data set, which, because it was so diverse, had different genders, different races, hair color.
Ethnic and everything?
Yeah, it was a really good diverse data set. So as we mentioned, there's around about 30 to 40, well in this case there was 40 attributes in this particular data set. Attributes can vary from your eye color to your hair color to whether you've got a beard. But for us, we were focused on whether or not we could detect it smiling, if we could determine your gender, and if we could then recognize you were part of a given database. The reason we chose, another reason, was that it was clearly well presented, well annotated, so we'd use that to help train the model. Just some example pictures that were in the data set. Okay.
Right. So, one of the things that we did was model selection, and as Scott mentioned, we chose to use a CNN. And the reason for that really is just because CNNs really have been proven to be very successful with image classification and identification. So that's why we kind of focused on a CNN. As Scott mentioned, we also had 3 different models. One of them was a very simplistic model, which was self-created. It only had, when we go over the architecture, it had like 4 layers to it. The idea to have a very simple one was that we wanted to like test it and try different scenarios with it to vary the hyperparameters and to kind of see actually how the hyperparameters were affecting the accuracy. We also had this, this pre-trained model, VGG16, which had a lot of parameters, lots of layers, And finally, what we did is we used a FaceNet model in order to actually try to detect whether a certain face belonged to a group. So for example, if you had a group of 30 people and you flashed up an image of a picture of someone and you wanted to figure out if they actually were a member of the group, you'd say, well, that's kind of what this last model did.
Who developed the FaceNet?
That was just like a model that we found basically on the internet.
I cannot hear.
A model that was found on, it was a pre-trained model,
Uh-huh.
yeah, on the internet.
Internet. So who is a commercial or the
Facebook's, I believe.
any university?
I think it was made Andrew Ng.
Ah, it's Andrew.
Yeah.
This. Okay.
So this is a picture of our simplified model. You know, there's 4 layers to it. We had, we had 3x3 filters. We also used max pooling, so we kept kind of reducing the image as we kind of progressively went through the structure.
So you have 2 convolutional layer
We had 4 convolutional
four.
layers.
and how many max pooling?
We had 4
For
max
for
pooling.
each.
That's right.
Okay.
One for
Then
each.
apply the activation function every layer.
Activation
Okay.
function every layer. That's right.
Then the final fully connected.
That's right.
Okay.
We flattened it and then we had a fully connected
Mhm.
layer. Yep. So
What's the size of the images?
the images
Universal
were
picture.
like 218 by 178 by 3. So
Did
that-
you use the GPU?
We did not use the
So
CPU.
it may take a much longer time than.
Yeah, it took, it varied, you know, it took on average 15 minutes to maybe 30 minutes. We didn't train a lot of epochs. We usually went, you know, epochs were maybe 10 to 15,
Mm.
at the most 25. So
Wow.
it didn't take too long.
Oh, really?
Yeah, I think the most it took, well, the VGG network took like 4 hours.
4 hours?
They had like 37 million parameters.
Mhm.
But most of the ones we had like 6 million parameters, so it didn't take too long. So we did a bunch of pre-processing as well. And so we kind of visually inspected the data, made sure there was no kind of missing information. All the data was pretty well annotated. The most time-consuming part was we actually kind of sorted the information into different validation, training, and test sets. So we kind of had like a loop that went through the code and actually took the images from a source file, and actually put them in, a validation, a test, and a training folder. So we tried to detect basically 2 different things on a face. One was a smile, and the idea with that was kind of like a narrow part of a face. It's really just a single feature, and so there's probably not a lot of information for that. It's just a narrow area. So the best we started, I think, with like 86% accuracy when we first started with this. We ultimately got up to like 91.8 accuracy in terms of predicting a smile on a face. What we found though was that for detecting gender, because there's actually more features to it than there is for a smile, that we actually were able to get much higher accuracy, up to 95%.
The smile is higher.
The gender was higher.
Agenda is higher.
Gender is higher, yeah, because it's more features as opposed, in a face. There's more like indicators, let's say, like you could have long hair or
I see.
things
Oh,
like
okay.
that. You know what I mean? As opposed to just looking at the lips. There's different features. So we're actually able to get a better, amount of accuracy.
What about age?
What's the age? We did not.
Do you
That was
think that it works?
works for age. We didn't try that actually.
But I just asking, based on your experience, last few weeks, the age prediction can be doable using the CNN?
I might. You would think so.
Yeah.
I would think because that's like a.
That's the experience, not always the CNN or the deep learning can solve all the problem, okay? But while you are implementing by yourself, you can see what can be doable, which one cannot be doable. And so that is the most important part you will get from this kind of project. Okay, go ahead.
So maybe just some of the results, and then we'll show like a demonstration of the models. But a couple of the key takeaways were, and a lot of these are things that I think we've all kind of seen ourselves, just in working with these networks. One of them was that the number of examples has a big impact on accuracy and overtraining. So at first we started with only 2,000 training examples, and we found that there was about a big difference between our validation accuracy and our training accuracy. It was like a 13% difference, which indicated overtraining. We then basically upped the number of examples by a factor of 4, and that basically eliminated the overtraining. What we then said was, let's just use all the possible examples. So we had like 160,000 training examples, and that's what brought us from like 86% accuracy up to like 91, almost 92%. We found the number of epochs didn't really have a big impact on the training. It was somewhere around 9 or 10 was kind of like the best. We tried 15, we tried 25. It didn't really seem to have much of an impact. We didn't go really high, like 100. We kind of stayed on the lower bound of it. In terms of optimizers, there's 2 optimizers that we tried. One was Atom, one was RMS Prop. They both happen to be very similar. One of them has momentum, the other one doesn't, so there wasn't really much difference in the accuracy of those 2. We did find though that when we basically went from, we increased our the Atom learning rate from like 0.001 to like 0.0205. We thought that would actually improve things, and it actually caused the model to crater. Our accuracy went from like 90 down to 50. We experimented with additional layers, not that many. We started with 4, we went up to 5 and then 7. That also didn't have much of an impact. We seemed to be, at least on the smiles, we were always in that 91% range. So that's kind of some key results. Maybe we could just show you a few, maybe like some some examples of it. So this is this kind of detects smiles. So this is kind of a test. So we'll just run it real quick. So there's the person, the test image. Looks to me like he doesn't smile. He's got his teeth showing, right? So here's what I don't know if you can see it in the corner here, but it says that he's smiling. But unfortunately, it only I would have thought that that's a very clear smile.
I don't think he's smiling clearly.
Okay, so
so 55 would make sense.
55% smile.
Yeah,
55%?
half smile.
You think? Let's try another.
The cheeks weren't up too much.
The cheeks. Let's try another.
He may not satisfy his results.
So here's another.
Yeah, definitely
Is
is
it
smiling.
So he's got a smile. 94%.
94.
Just for the heck of it, we'll try one more. I don't know what you think. Is that the smile?
It's kind of smile. That's the smile, the eyes.
65%. Okay, so, and then we'll just take a look at the gender. So here's the gender one. So now she has short hair, right? So that comes in at only 55%. Now let's try another.
55% of female. Okay.
55% female.
It's not 55% of a female.
Try another picture. He's got a mustache, short hair, but he's not really looking straight at us. Okay, 94%. We'll try maybe one more, and then we could just show the other model. So So. Okay, it's short hair again, 58%.
So, why did you guys go with the percentage instead of like a binary model? Since we only tested like male or female, smiling or not smiling.
Right, it's a good question. So when we were actually doing like the training and the validation, that's exactly what it was. It was binary. It was, there was basically a 1 or a -1. So 1 was, the feature was there, a -1, the feature was not. So that was like a separate, let's say, model. And then when it came time to the actual test, so this is like the test part, this is just kind of showing, the test.
So you want to do like the, I guess the variation on the error while you're actually looking at it?
Yeah, it's kind of like doing almost like, yeah, like it's almost like we use a softmax, I guess, for this instead of a binary. So, and then the very last one, it actually takes quite a while to run. So we just kind of printed out a few things, but so what we did is like we fed an image. So we, Arnold. Here's a picture of Arnold. We fed that, and it's a 96 by 96 image. We had a database of 30 images. These are the faces in the database. And then, so there's the screenshot says, the result is it's Arnold. The distance measured is 0. We fed in another test image. This is Mark Wahlberg. Again, 96 by 96. That came out fine. And then what we did is the last one we fed in an image of someone who was not in the database. This is kind of a random person, and it actually shows up that he was not in the database.
Okay, let's stop here. Thanks so much. It's very nice. Okay. The next team, the team 5, the identity setup. My only point is please use the bigger font size when you present. It's very hard to read. And also I suggest I know